Okay, just a brief disclaimer. So the numerical values that you will see during this presentation, they are here only for comparison and illustration purposes. Please do not use these values as a replace of your actual commissioning measurements specific to your machine and treatment planning system. So today we're gonna have a brief conversation or review about the dose calculation methods, specifically to model-based ones. We're going to talk about the data acquisition that we need to do beam modeling and how we do the data input into the treatment planning system. And then we're going to talk about the validation. Okay, so for model-based methods, we know that they are based on pencil type of kernel, or they can be point-based. We also have the grid-based Boltzmann solvers or the typical Monte Carlo. So for pencil beams kernels, this one use a superpose a predetermined dose distribution from very narrow beams of radiations in water. And an example of this type are the pencil beam calculation algorithms. However, these ones are not very good, at taking into account the scatter, and therefore they are not that accurate. We have the point kernel based, and here the dose is modeled based on a pre-calculated heterogeneity scale point kernel. And as example, these are the convolution superposition methods like AAA from Varian, or also use a type of convolution superposition methods. And there is some kind of new one, the grid-based Boltzmann solvers. And here the dose is calculated from numerical solutions of differential equations. And as an example is Accuracy from Varian. And then we have the Monte Carlo, which of course is the more accurate one because it simulates the particle transport. So what is the meaning for these model-based methods? When we're working with model-based methods, we need to do something that we call beam commissioning. And beam commissioning refers to setting parameters that is going to describe the quality of the beam that we are using. For example, the source size, the lateral fluence, the penumbra of the beam. And all the data that we measure to commission these model-based calculation methods, we need to input that data into the treatment planning system. That's why it's very important that the beam model should be performed by a qualified medical field. Now, I have a question, and maybe there is no wrong answer here. It's just to gather some information about if you have experience doing this exercise before or not, and if you have read something. Maybe if you can type on the chat your answer, and then maybe Tulasi or John can give me like the majority of the answers. So what data do you use for commissioning a new dose algorithm? One, you measure the data according to the vendor's guideline. You use a golden beam data, or you partially collect recommended data, or you measure all the data according to the vendor's guideline, and more. Do we have any answers, John or Tulasi?
It seems like most people are saying number 4.
Okay, that's great. So we can either measure the data according to the vendor's guideline, or as in my institution, we measure all the data according to the vendor's guideline and more. And when I say more, it's because we have, we have another algorithms that we use to cross-check our MU values. for each case that we do in the clinic. So please never cut out data. Okay, so for data acquisition, and this is based on my experience at my institution, we don't use the golden beam data. We acquire our data according to the vendor guidelines. We read the manual and we use, for example, the task group 106 before we start getting all our measurements. And there is also the AAPM practice guideline number 5. They have developed a very nice suite that is an open source that you can use to commission in QA the treatment planning dose calculation for photon and electron beams. And my recommendation will be that you have a folder for each energy that you are trying to commission. So it's more organized. So you don't have a big folder with all your energies, because then it gets very messy. Also, what we do after we take our data or we do our measurements, we compare with peer review publications. We compare output factors, scatter factors, PDDs, and TMR. And we also use the BGR 25 data. So this is a table from the medical physics working group number 5 on the recommendations that they give depending on the data that you want to acquire. And I wanted to add this table here because it's very nice, because you can go back to these different references. And also they provide some recommendation based on the equipment that you need. And we review the equipment that you need and that I use, for example, in my clinic in our previous session. So for example, for ECLIPSE, in my clinic, we are all variant. And I have to say that I don't have any economic interest in variants. So this is a full disclosure. I'm not encouraging that you buy variant products or anything. This is just what we have in my institution. So according to variant, when you want to commission a dose algorithm in ECLIPSE, you have a certain minimum requirements. For example, the recommended data for your PDDs and profiles, they recommend that you take data from a 3x3 to all the way to a 40x40 field size. And they recommend that you must have a 10x10 field size. You don't need to acquire a 2x2 PDD or profiles, because it's not taken into account into the configuration. And also, they recommend that you take diagonal profiles for the maximum field size. In this case, will be the 40x40. When we do the commissioning, we take the 40x40, the 35x35, and the 30x30. Even though we don't put it in the treatment planning system, we have it because then when we do the annuals on our machines, we use these scans to compare. And also they recommend that we take the output factors from 3x3 field size all the way to 40x40. You don't need to acquire, for this particular treatment planning system, field sizes smaller than 2x2, since this is not gonna affect the calculation results in your system. So imagine that you have acquired all the recommended data that you need. And now it's time for you to import this data. In this example that I'm giving you is for ECLIPSE. So you go to Beam configuration.
Oh.
Yes.
From your previous slides regarding the ECLIPSE, because I have an experience with the ECLIPSE, that is it interpolating? I know for the lower values less than 3x3. So does this interpolation is just a linear interpolation, or is it what kind of interpolation it does?
I think it's linear what it does, but you know what? Since I haven't done this in some years now, let me get back to the manual, and then I'm gonna email you my response.
Yeah, the reason I'm asking is that if it does the linear, so it's very difficult because now it cannot apply because of the small field. There are so many things involved here. Yeah.
Yes, and that's why it's better if you want it to be more accurate, then it's better for you to measure it. But then if you measure it, you have to keep in mind that you need maybe a diode or a very small cavity ion chamber. Yes. Okay, so now imagine that you have acquired, and my recommendation will be that you focus first on acquiring all the data that you need for your treatment planning system, for your algorithm. That you make sure that you have all of these measurements before you start building your beam model. So now when you go to the beam configuration tab or module, you know, it's organized. As you can see here, let's say that we want to work on my 6x energy beam first. And you have to do this for each energy, okay? Then it's gonna ask you, you know, import the measure depth doses. In this case, I'm just showing the 30 by 30 field size, but remember that you are gonna import all the way from 3 by 3 to 40 by 40. And then once you are here, please make sure that you review the data just to make sure that it was properly imported. That, you know, for any reason it's not corrupted, or, you know, these are computers, right? We have to make sure that when you do the import, that nothing was messed up or you made a mistake that you bring to your treatment planning system the incorrect data. Once you have all your data, your measure profiles, your output factors, your measure diagonal profiles, you need to do what is called the beam data calculation. And then you need to do some beam analysis. And this is happening, this is still on your beam configuration module. You haven't left that particular set of your treatment planning system. And then here, what is nice is that it's showing you what you measure, in this case in red. And then based on all this data that you feed it with, it's showing you the calculation, like what the treatment planning system is calculated out of the data that you just measured and you imported into the system. So it's very nice that you make an analysis, you know, of the parameters. Here in this step, you can tweak it, you can try to modify a little bit if you want it to be more, you know, accurate and precise. Remember that when you are modeling the beam, this is a iterative process. You might need to go back and tweak again. And why do I say that? For example, when we commissioned our machine in 2017, we measure from 4 to 40, okay? And here is the ECLIPSE process data, and this is what we scan. You can use, you know, Excel sheets or now you can use the WAPM working group. They have a very nice lab implementation where it will do all of these comparisons for you. And, you know, we have some tolerance here. It's very important that you document all your process. So if you want to go back, like me, I wanted to go back 3 years now. on what we did and how we did it, it's very nice that you have all your documentation. Even here, I wrote down the type of ion chamber that we use, the water tank that we use, and how the measurements were performed. Also, we went back and we used, some of the published data available. So we compare from a paper from Chan. This is a measurement from a true beam machine, a 6 MV beam, a photon beam. And as you can see, this is the difference from our PDD being modeling from Eclipse from the paper from Chan. And we were very happy. I mean, for the 40 by 40, we have a half a percent different, but this is what you expect for big fields. And also we use the true beam representative data from Varian or the golden beam data. We also want to compare, like how much is our beam modeling of from the golden beam data. This is just to reassure that your measurements are within tolerance compared, to your peers, compared to a Varian golden beam data. It's very nice to have redundancy because then, you can have a very relaxed mindset that everything that you did is fine.
Paulina, I think this is a good time for a question that was just asked, which was what's the problem with just using the golden data, as for your beam model? And I think you kind of addressed that, which is that, you're not actually checking to make sure that it holds true on your machine if you're just taking it for granted.
This is a very good question. There is nothing wrong with using golden beam data. In my institution, it's our preference, and if I go to another institution, that will be my preference too, based on my experience. If you end up using the golden beam data because of time, because to do a commissioning takes like 6 weeks. And when I did this, it took us 4 weeks, including the weekends. We were working 12 hours a day. And for this machine, we didn't have electrons. So that's why it took us 4 weeks. If you use golden beam data, please make sure that you go back and you do some checking, right? You want to go back and still do some measurements to make sure that it's what you expect. It's not that you are just going to use the golden beam data, put it in your treatment planning system, and start calculating and treating patients. You still need to go back and you need to put your water tank and do some measurements at a different field sizes, depth, and you need to do some type of comparison.
Paulina?
Uh-huh.
Just a comment, because I don't know the exact name of the TG, whatever, the AAPM report. They're not recommending to use the golden beam data.
Oh, yeah, TG, they don't recommend, they don't. But there are some places, and I have colleagues that they have used it. This is, this is based on personal experience and preferences. But if you end up using the golden beam data, you are responsible for going back and check different PDDs at different field sizes, at different depths. You need to do some type of calculation because you are just blindly taking for granted the data that was given to you. And that's not recommended. In my experience, I will prefer to do all my measurements, even though it takes time. But I understand that there are some places, that they don't have the manpower. Sometimes you end up working on a solo physicist facility. For those places, if you have colleagues, ask them to check it for you. You need to have some type of redundancy. I'm not recommended that you use the golden beam data, but if for any reason you use it, you are still responsible for going back and doing some measurements. You need to do some comparisons. Okay, so this is another example of some measurements that we did after we imported our field data. We put the, water tank, and we use a farmer chamber. And we did this for a bunch of field sizes because we want to make sure that for the basic photon beam open fields, here we haven't introduced the MLCs yet, because we want to make sure that the beam model, it holds for the basics, for the most simple one. And then you are going to start introducing your wedges. And then you are going to do more validation. And then you are going to introduce your MLCs. And then you're going to do some validations. So what happens if you introduce everything at once, the wedges and the MLCs, and you start to do your validations? You don't know from where your errors, if there are any, they are coming from. So that's why it's important that you do this exercise or this implementation in step by step. So you make sure that when you encounter a problem, it's because you are introducing a new parameter. It's not because you have all the parameters at once. Otherwise, it's going to be very, very challenging for you to discover from where the error is coming from. Okay, so we did these measurements from all the way from 6 by 6 all the way to 40 by 40. It's a long table. We use, Excel spreadsheets to keep all our measurements. And also, since in my institution we are a big group, I was responsible for acquiring the data, and then another physicist was importing the data into the treatment planning system. So we were doing, and then we had another colleague doing some independent validation. So, and we do it this way to, because I'm biased to what I measure. So we're trying to do some independent checking within our physics group, okay? And we did this for each beam energy, this type of measurement. And now, we introduce the wedges. In my institution, we don't have physical wedges. We have the enhanced dynamic wedges, but we still do measurements on it. As you can see here, we did measurements for 6x and 15x for different wedges, for all the wedges that we have at 10 cm depth and for different field sizes. We do measurements for when you are at central axis and what happens if you are off axis. And we documented every measurement, everything that we did, the detectors that we use, the persons that were working for these measurements as well. So we know who is involved doing what and when. That's very important that you keep documentations. Also, we did, TMR validation. As I said before, on this machine, we don't have electrons. We were only commissioning photon beams for this machine. And here, you can see all the detectors that we use and what we apply. And here you can see the difference. This is our treatment planning system, and this is our actual measurements in water tank, and here are the differences. And here, we have our tolerance, like what we take as an acceptable and from where we're taking this tolerance from. Now, it's very important that when you do your commissioning and you perform your TG51, when you adjust your output to the machine, it's good that you keep a record. We did it like after I did my TG51, we were doing output measurements almost every day because we wanted to trend the output of the machine. This is just as a safety.
Paulina, just one more question from your previous slide. I can understand that you have done all this in a homogeneous phantom.
Yes, this is in water.
Validating in inhomogeneities as well?
Yes, and I will go there. Yes, so as I said before, you know, we wanted to make sure that all the data was holding, you know, in water, because then if we spotted an error, it's easier for us to go back to the treatment planning system and try to understand why we were getting the discrepancies. But in our case, we were satisfied with our results. And then the next step was introduce the heterogeneity. And to do that, we used the Sears phantom, and we used the TRS 430 from the IAEA. And, you know, they explain, or they have like a suite of different type of cases that you can plan. And here, I mean, you can go back either to the TRS 430 document, but I'm telling you like an example here. These are all the energies that we had available on our machine. And this is case, let's call it number 1. And it's very nice because it shows you the location that you can put your ion chamber. So here we are going to be doing heterogeneity measurements. And these tolerances, they are coming from the TRS 430 document. And as you can see, this is our calculations from our treatment planning system. And this is what we measure at the machine, and these were our percent difference. And we, you know what, we were very satisfied with our results. And this example is taking into account the wedges. I think that if you go back to the TRS 430 document, it has more than 10 different cases that you can plan on your treatment planning system. Then you go back to your machine and you do actual ion chamber measurements. So when we do this, we take, you know, we take like baby steps. We acquire all the data, we feed it into the treatment planning system, we go back to the water tank, it's only water. We make sure that the PDDs, TMR, that all our values are matching the treatment planning system. Then we tested the wedges, and then we test the heterogeneity. And now we are gonna test the MLCs. Because as I said before, if you feed everything at once and you start getting discrepancies or deviations, it will be very hard for you to know from where these errors are coming from. Now, the MLC data that is required, it depends on your treatment planning system. But before, you need to get familiar with your MLCs. So the TG72 has the basic application of multi-leaf collimators. It's very nice that you go back and you read it. Some of the treatment planning system, they require the MLC transmission factor, the dosimetric leaf gap, in the case that your MLCs have the rounding edge. And here, you know, different companies or different vendors, they have different MLC design. For example, you might have the upper jaw replacement, and this happens on your Electa machines. So for the Electa machines, the MLC leaf move in the Y direction. You have a backup collimator. You have a small range of motion. You have a more compact treatment head diameter. The MLCs are far away from isocenter, and therefore the smaller leaf width and leaf travel is very, very tight. There are other systems like Siemens, where the leaf ends are straight. I'm more familiar with variant machines, where the MLCs, they are known as tertiary collimators. The MLCs are located below the jaws, and they use a rounded edge leaf because they provide a constant beam transmission. However, this increases the diameter of the gantry head, so you have to be mindful about clearance issues at the machine. Now, according to task group 50, there are some properties that the MLCs, that they're required from the MLCs. So your upper or lower jaw replacement, they should have the same as the collimating jaw. So the transmission should be around 1%. If your design is a tertiary design, like the variant machines, this should be less than 5% or within 4 to 5 half value layers. So for interleaf transmissions, the MLCs are focused in the perpendicular direction of the leaf motions, and the leaf may have some overlapping component to decrease the interleaf transmission, as is the case for the variant machines. And now you have your leaf end transmission. So the leaf end transmission is defined as the dose that is reduced, measured along the rate passing between the ends of the opposed leaf in their most close positions. And here, this is a table comparing the Electa, Siemens, and variant manufacturers. And this table is coming from the TG50. So now, I'm using, Eclipse because this is what I'm familiar to. For Eclipse, the MLC data that is required is the MLC transmission factor, gap, and it's very important that you are precise when you are measuring, because this has a dosimetric consequences, and they can be quite significant. For example, imagine that this is your nominal leaf gap value on the x-axis, and this is just your dose error in the y-axis in percentage. So let's say that you have a 1 millimeter error and your nominal leaf gap is 1 cm, you can see that you might end up like with a 12% difference between your delivered dose. So it's very important you are very careful when you are measuring the DLG values. This is an example of, I was doing a commissioning for another system that we use to cross-check our MU calculations. And I just put it here as an example. I variated the DLG values from minus 0.5 millimeters to 0.5 millimeters and not centimeters. And we were getting about 3% different. And you might think, oh, but 0.5 millimeter is tiny, it's not much. It might end up being quite significant. So be careful when you are doing these measurements. Also, make sure that you do some testing on your MLCs. That you do some picket fan test every month. And we do it every month during our monthly QA, and we check it every Friday as well on all of our machines. So for our measurements, we use the DLG procedure according to variant, and variant provides you with a XML DICOM files, and everything is programmed on these files. So our measurements were acquired at 95 cm SSD and 5 cm depth in water and we use an ion chamber. We use the A12. And here, the way that this is measured, you have like a tiny slit or gap starting from 2 millimeters all the way to 20 millimeters. And basically, you are putting your ion chamber on the central axis. And then you are doing some measurements when you are, you know, when you have a open versus a closed or very tiny gap. So this is an exercise that Varian is written a procedure on it, and we follow the procedure. Also, after we did these measurements, you go back to your treatment planning system, you enter this value here, but then you have to start, you know, planning, and you need to do some validation tests. For example, these are some preliminary results that we have on long case. And if you see here, we had a field where we end up seeing a 6.8% difference. We weren't happy about it. So we went back to the treatment planning system, and you need to adjust this value. So sometimes you have to, your good start is your measurement, but then again, you calculate and then you need to validate. And then if you are not happy or satisfied with your results, you know, you do an investigation. Where is field number 4 coming from? Is this what I expect? Based on the recommendations from the IAE protocol, we weren't that satisfied. So we adjust a little bit the dosimetric leaf gap, and we repeated the exercise. We recalculated, we went back to the machine, and we did more measurements. So you have to be redundant. You have to acquire a lot of measurements.
Paulina.
Uh-huh.
Yeah, here, should we rely on our treatment planning system or the detector we have measured? So it will be, I mean, the tweaking the value is a bit tricky, so.
Yes, so the measurements is a good start for you. You put your measurement there, and then you calc a simple plan. When we started with a plan in the mediastinum. Can you see my mouse?
Yes, yes.
Okay, so we started with a plan in the mediastinum here, and we were very satisfied. Everything looks, you know, was holding within 3%. We were happy. And then, you know, you start introducing complexity, right? So what happened if we measure in long? Because we know that now you have, you know, your electron disequilibrium there is more complex. Then we weren't happy about this 6.8 result. So what we did, we went back to the treatment planning system, and we changed a tiny bit the DLG. We repeated the exercise. We calculated again on the treatment planning system. We measured in mediastinum first, and then we went back to the same long case, and then we were satisfied because I think I don't have, let me see if I have the results here. I don't have it, but we were below 4%. So we were happy, and we were within the tolerance that the TRS 430 was recommending. And also we went back to the literature, you know, comparing DLGs that you measure, but then there are multiple papers where they end up using a slightly different factor, because it's never, I shouldn't say never, but sometimes it doesn't quite work as well. The value that you measure with the value that is really needed in the treatment planning system. And then in our clinic, we use a lot of VMAT. we are a very busy department. I think that we have on treatment 170 patients. So we start treatments at 8 in the morning all the way to 7, sometimes even later at night. So we rely heavily on VMAT. And as you can see, we were happy with our results for VMAT and different energies. Remember that you have to do this test for every energy that you commission. Let me see if I have. Yes. So here are all the plans that we did. And for this test that we have here, these tests were performed using an ion chamber and the Sears phantom or a heterogeneity type of phantom. Now, we use for this IMRT and VMAT validation, we use the map check and the R check phantoms. And as you can see here, these are for the seed sets. We have esophagus type of cases. So we plan for esophagus, head and neck, lung, prostate, SBRT, and the list goes on and on. And here you see the different distance to agreement and gamma that we use. We use 3%, 3 millimeters, and 2%, 2 millimeters. These are quite more tight, but it's to do this validation, it took us like maybe 8 hours taking data and doing analysis. And as I said, it's very nice if you can involve, a colleague that is not, that wasn't part of your initial data acquisition. So you have somebody with fresh eyes that can review your measurements. Redundancy is good when you are doing BIM modeling and commissioning a machine. So in our institution, we do independent dosimetry check. Another physicist is bringing to the, into the party, and we said, okay, can you please do these measurements and give us your results? Also, we do IROC, output check. We don't go live until the machine, until we have an independent audit on our machine. So we use IROC from MD Anderson to check our output. Also, we use IROC Houston, the head and neck phantom and lung phantom to do, an independent checking on our system. And for example, MD Anderson, when they ship the phantom to you, they tell you how do they want the plan and how you are gonna do the delivery. So it's very convenient and it's very complete, and then you have a good set mind. You can go home and sleep well that you did what you were supposed to do, that everything is properly measured and somebody else checked it for you. So I'm gonna conclude that please follow your treatment planning system vendor data acquisition recommendation. Never ever cut off data recommendations. Compare your measurements with your treatment planning system model. You can use in-house testing. You can use ion chamber plus a phantom. Let's say that you don't have the Sears phantom for any reason. You can use solid water, and you can buy cork. Cork might simulate, air. And so you can, be creative. You can use films as well. The films is going to take more time, but if you don't have an array like map check or R check, you can use films as well. It's going to take you a little bit more time, but it's the time that is need to be taken in order that you have a safe commission of your machines. Rely on peer review audit. In our case, here in the US, we rely on IROC and MD Anderson, and it's part of our policy that we don't go live until our machine is audited. When we get the results, then we can tell the physicians the machine is ready to treat patients. And you know, and you keep an eye on your machine's output, especially when they are new, you know, because the ion chambers might drift a little bit. So if you have any other questions, I'm very happy to answer your questions. Thank you so much.
Thank you, Paulina. That was fantastic. I had a couple questions that were submitted that I was gonna, we could take now. We had someone ask, why do we always have to use square fields for performing beam data collection? And why not use rectangular fields?
For commissioning, remember that the data is gonna depend on the vendor, what the treatment planning system requirements are. You are free to take more independent for you to have it as a reference for later, for your annuals or for your monthlies or for any check that you want to do. But keep in mind that the treatment planning system is expecting a particular file, and that's the way that you should do your measurements.
Okay, great. And we had another question. What would you recommend people do if they don't have a heterogeneous phantom?
So, you know, if you don't have an heterogeneous phantom, as I was saying before, you can just, you know, be creative. You can use solid water, but then you need to have some type of material that maybe you can place or like a sandwich, right? Between solid water and your ion chamber. It might get tricky because when you are using another type of material, you need to be able to stick your ion chamber at different locations. So that's why this phantom, the medical physics, the MPPG5, they have a very nice suite, and they have examples of other type of phantoms that you can develop in-house. And I think that they use a combination of solid water and cork, and there are other type of plastic that you can use. But with the caveat that then you need to, you know, machine your ion chamber so you are able to stick it inside.
I think even they can put the styrofoam. From my experience in my center, there was no heterogeneous. I made the holes with the styrofoam and they make it inhomogeneous in between the solid water phantom.
Yeah, like a sandwich, right? Okay.
Any other questions from anyone? All right. Well, it looks like that's everyone. Paulina, thank you so much for taking the time to go through some of this with us. I found it very useful, and it seems others did as well. Again, as a reminder, we'll be posting these videos a few days afterward to the YouTube channel. On Monday next week at the same time, we're going to start our section on QA for IMRT. Dr. Bob Price from my institution, Fox Chase, will be talking on Monday, and then the session on Thursday, which will be kind of an interactive session talking about how each of you do QA at your institutions and maybe having some submissions of data potentially. We'll explain that a little bit more on Monday during the session. So, and if you have any questions, please let us know via email in the meantime. And otherwise, thank you everyone for attending. And thank you again, Paulina.
Thank you, everybody. Have a good day.